So let's go over what's due on Tuesday, which is when a whole bunch of stuff is due and when our test is. So worksheets 21 through 24 are due on Tuesday. They're quizzes on Brightspace. They're in the worksheet section of content as well. And homework number 1 is due on the 23rd. This can be turned in on Brightspace or on paper in class. It's an assignment on Brightspace, so you can submit it as a file on Brightspace. Or if you're writing it up on paper, you can just hand it to me in class. And the worksheets for the next set are going to be due on the 16th. Our first exam on chapter 1 and chapters 21 through 24 will be on the 23rd in class. It's 60 multiple choice questions. You're allowed 1 sheet of notes, double-sided, to use for reference. The test will be in class on paper using a Scantron sheet. That means you need a pencil. Technically, you need a number 2 pencil, but pretty much every pencil on the market these days is a number 2 pencil. I will have some for people to borrow, but please try and have a pencil. And if you have accommodations, I believe you need to make an appointment with the Access Center and you need to do it probably today. I've been talking with them about that because I know there's a person in this class who has accommodations. Any questions about anything about the test or anything like that? Yes.
So it's just like generally about everything we've been.
It's about chapter 1. It's a few questions from chapter 1 and mostly questions from chapter 21 through 24. So mostly on the astronomy stuff we've covered, with a handful of questions from the first chapter. That should be all pretty straightforward. I think I only put in 5 from chapter 1 and the rest are from the astronomy chapters. Any other questions? You will have all class to do it. So an hour and 20 minutes. I'm gonna get started on the lecture. So we've been talking about heating the atmosphere, how the atmosphere gets heated. Well, the primary source of heat for the atmosphere is the sun. The sun is pumping out energy, lots of energy, and it's spreading out in all directions. And the atmosphere is mostly transparent to incoming solar radiation. It absorbs some high energy stuff. It absorbs like some infrared, but it's more or less transparent to where the peak of solar radiation is. So that will all come in and reach the ground. There are a few different atmospheric effects that affect what happens. There's reflection. This can be measured with albedo, the percent reflected. So I believe Earth has an albedo of around 50% maybe. It reflects about 50% of the light that comes to it. Might be less, might be closer to 30. And while say Venus has an albedo of 70%, and the moon has an albedo of like 5%. It's actually really quite dark. Then there's scattering. When light enters the atmosphere, it is scattered. This is why the sky is blue, for example. That is light traveling from the sun, striking the atmosphere at an angle and being scattered back to your eyes. And shorter wavelengths scatter more than longer wavelengths. And then lastly, there's absorption, where the atmosphere will absorb some wavelengths. Most visible radiation makes it to the surface. The atmosphere is transparent to visible light. and about 50% gets absorbed at the Earth's surface. So about 30% bounces back, is lost to space by reflection and scattering, so the albedo is somewhere between 30 and 50%, depending. 50% gets absorbed by us. Some percentage gets absorbed by the atmosphere and clouds. Let's see. Okay, yeah, the albedo is about 30%. That's the amount that gets reflected. And then you look at something like Venus, where the albedo is like 70%. Reflects a whole lot more. So of the absorbed 50%, that warms up the ground, and then the ground will re-emit at longer wavelengths because it's now warm. And that's what gets trapped by the greenhouse gases. So this is a short video about the paths that solar radiation takes and how it makes it to the surface and how some of it leaves.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the different pathways that incoming solar radiation may take when it hits Earth's atmosphere. You're probably aware that different objects reflect light differently. So some objects tend to absorb more of the light that hits them, and others tend to reflect more of the light that hits them. Some of the different substances on Earth that are part of our climate system are shown here in terms of their reflectivity, or albedo. You can see here that thick clouds will bounce off about 70 or 80% of the light that hits them. Grass will bounce off about 5 to 25% of the light that hits it. Light-colored roofs will reflect away about 35 or 50% of the incoming light that hits them, whereas dark roofs are more like 10 to 15%. Asphalt is almost like a dark roof. It's like 5 or 10%. If sunlight hits water, it can be absorbed almost completely, which is only 5% being reflected away, or it can have a lot that's reflected away, or up to 80%. And that basically depends on the angle that the sun hits the water at. You probably experienced that if you've ever stared into a sunset across an open body of water. Sandy beach, around 20 to 40%. Wet plowed fields, 15 to 25%. Forests tend to absorb most of the light that hits them. They only reflect away 5 to 10%. Snow reflects away a lot, 50 to 90%, and thin clouds around 25 to 30%. Incoming solar radiation can take one of several paths. About 50% of it enters the Earth system and is directly absorbed by either the land or the sea. Of the 50% that's not directly absorbed, several things can happen. One possibility is that it's absorbed by the atmosphere or the clouds. Another possibility is that it's reflected from the land-sea surface. An additional component is reflected from the tops of the clouds back into space, and then there's some that's actually backscattered to space by the atmosphere as well. So that means that a total of about 30% is lost to space by reflection and scattering. So basically, if we're losing about 30% to space and we're absorbing about 50%, that leaves about 20% remaining that is absorbed by the atmosphere and clouds. And that's the important component of the sun's energy when it comes to discussing climate change, because that's the part that's being amplified in the current system. Can you think of any way to cut down on the amount of radiation that makes it down to Earth's surface? Well, one way to do that is by erupting a volcano. Volcanoes tend to put lots of sulfur aerosols into the atmosphere, and it creates a sort of haze. So here in this picture, where you can see the sort of yellowish gray haze there, that is coming from a volcano in the Philippines. And when these volcanoes erupt, they can really end up cutting down on the amount of sun that actually makes it to Earth's surface. So here are the eruptions of two volcanoes, El Chichon and Pinatubo, and their effect on the amount of solar radiation that made it to Earth's surface. You can see that El Chichon made it go down by about 4.5%, whereas Pinatubo reduced the amount of incoming solar radiation by about 3.5%. So these are significant effects. Thanks very much for your attention. This has been another Smart Figure.
And that reduction in sunlight coming to the surface is what I mentioned before as that year without a summer that happened. That was in 1815 or 1816. It was caused by the eruption of Mount Tambora in Indonesia in 1815. It just threw up so much material that it disrupted, the climate around the planet. So here are some of these examples from the video of the albedo's reflectivity of various surfaces. So different surfaces reflect more or less sunlight. That's one of the reasons, like, snow and the ice caps and such reflect a lot of sunlight to actually help cool the earth when you have more snow and glaciers and things. So the earth, once it absorbs energy, it re-emits that as at longer wavelengths. And these longer wavelengths, terrestrial radiation gets absorbed in the atmosphere by carbon dioxide and water vapor. And other things, but those are the two biggest contributors. And this heating of the atmosphere is termed the greenhouse effect. And at the moment, Earth has got a level of greenhouse effect that is reasonable for human life. We don't want to have too much, and we don't want to have too little. Because too little, Earth gets really cold. And you get something like Mars. Mars is basically no greenhouse effect. Too much, you get really, really hot. You can get somewhere like Venus, where a runaway greenhouse effect basically cooked off all the water and released even more greenhouse gases and superheated the planet. But at the moment, the problem is that we are increasing it because we're releasing more carbon dioxide and other things that absorb radiation, and this is warming the Earth. I mean, not a huge amount, but it's enough to have significant effects. Especially because it's putting more energy, it's putting more water vapor in the atmosphere and more energy into storms and things like that. So this is the greenhouse effect. If you have an airless body like the moon, there's no greenhouse effect. All outgoing long-wave energy is re-radiated back out into space. You get a much lower average temperature. With a modest amount of greenhouse gases, you have a nice balance. Some outgoing long-wave radiation gets absorbed by greenhouse gases and then re-radiated back towards the Earth, keeping the Earth's surface warmer. With lots and lots, most outgoing long-wave radiation is absorbed by greenhouse gases and re-radiated back to the surface, and that gives you Venus, which is super hot and unpleasant. So we can look at 3 different planets and see how the
Hello, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at the lessons from 3 different planets. And after watching the video, you should be able to describe how the greenhouse effect works or doesn't work on the Earth, Venus, and the Moon. So here's the figure in your textbook that sort of takes a look at these different lessons that these different planets can teach us. Technically, I guess the Moon is not a planet, but let's go ahead and begin there. The same sort of lessons that the Moon teaches us can also be learned from the planet Mars. Basically, the sun gives off a lot of radiation. That radiation basically is absorbed by the surface and then re-radiated up, and there's nothing to stop it. So basically that energy is lost to outer space, and the Moon is very cold on its surface as a result. Now on the Earth, that same story persists, okay? Incoming radiation from the sun, re-radiated back up, but some of it is going to end up being caught by greenhouse gases, and that energy comes back down again. And so that's the reason that Earth is not as cold as the surface of the Moon. In fact, it's a very nice moderate temperature, which is just right for liquid water and therefore for life. Now in the case of Venus, the sun is shining on Venus. A little bit of that energy gets through Venus's very thick atmosphere, which is very bright, so a lot of it is initially kind of bounced off the surface of Venus. But of the portion that makes it through the atmosphere down to the surface, energy is re-radiated back up and it's absorbed by greenhouse gases, and basically most of it ends up getting returned. So basically Venus is really, really hot on the surface because it's got such a pronounced greenhouse effect. So now that we've considered the role of the greenhouse effect on the moon, on Earth, and on Venus, can you tell me whether the greenhouse effect is a good thing or a bad thing? Well, it's kind of a trick question, right? Because it isn't actually good or bad, it just is. And so on planets or moons where you don't have much of a greenhouse effect, it's too cold for life. On planets or moons where you have a really super runaway greenhouse effect, it's going to be too hot for life. And so a moderate amount of the greenhouse effect is actually a good thing because it keeps your planet warm and toasty. Thanks very much for your attention. This has been another Smart Figure.
There is some indication that Mars used to have a good greenhouse effect, but it lost most of its atmosphere and then got cold because of that. So, one of the things we record to understand what's going on with the atmosphere and understand our weather is air temperature data. So this includes things like the daily maximum and minimum temperature. You could also measure the daily mean temperature, that's the average temperature, the range that temperature goes through during the day, the monthly average, the monthly mean, the annual mean, the annual yearly average, and the annual temperature range. You can look at how temperature varies day to day. You can also look how it varies over the year and things like that. So these are some other calculated values. And if we want to look at how temperature varies over space, we can draw a map using something called isotherms. Iso means same, therm means temperature. So isotherms are lines of constant temperature. So they're lines of connecting points of equal temperature on a map, and they're used to show the distribution of air temperature. It's like a contour map, but for temperature. And the temperature gradient is the amount of temperature change per unit distance. That, is how fast the temperature is changing over space. So here's an example of a map with isotherms. You can see each line is labeled with a temperature. This line is 20 degrees. This is 30, 40, 50, 60, 70, 80, 90. Here it's colored in, it might be a little easier to see. Where this area is the 10s, the 20s, the 30s, the 40s. Where the lines are close together, temperature has a very high gradient. Temperature is changing quickly. So over here, temperature is changing quickly over space, while over here, it's changing more slowly. So this is just a way you can represent how temperature varies over, a map. So this is a short video about how isotherm maps work. And you can you can put other quantities on a map with lines of constant value. There are isobars, which are for pressure, to go with isotherms for temperature.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe what an isotherm is and how isotherms are depicted on maps. On any given day in America, it may be hot in some areas and it may be quite cold in other areas. One way that we can very succinctly communicate where it's hot and where it's cold is with an isotherm map. So here's some temperature data for different cities in the United States, Mexico, and Canada. And you can see that some of them are colder and some of them are warmer. In order to turn this spread of data into a picture, we need to draw lines that separate temperatures of different values. Rather than like connecting the dots or something like that, what we want to do is draw little imaginary fences that separate, say, the 70-degree temperatures from the 60-degree temperatures, or the 60-degree temperatures from the 50-degree temperatures. So here we've drawn a series of lines. So you can see, for instance, there's only one temperature on the map that's greater than 90 degrees in Monterrey, Mexico. So the 90-degree isotherm basically wraps around Monterrey like that. Then you can see that Houston, Montgomery, and Miami are all in the 80s, as is Myrtle Beach. So basically this 80-degree isotherm separates those values that are greater than 80 from the values that are less than 80 everywhere else on the map. Similarly, you can see there are lines for 70 degrees, 60 degrees, 50 degrees, 40 degrees, 30, and 20 degrees. That basically organizes all of this data into a big picture. So you can see that basically it's really cold up here in this region of Canada by Regina, Saskatchewan, and Bismarck, North Dakota. And it's relatively warm, of course, down in the southern part of the states. What would make this even more of a picture? What could we add to this to make it even more visual and intuitive? Just at a glance, you could see where it's hot and where it's cold. Hopefully you answered color, and indeed, if we just add color to this, the temperature patterns really pop out. So here, basically where one color meets another, they're meeting along an isotherm. The red blob down at the bottom, that's basically showing where the temperatures are greater than 90 degrees. The orange is temperatures between 90 and 80 degrees. Yellow is somewhere in the 70s, between 70 degrees and 80 degrees, and so on. So in this way, you can really see that there's this great big cold blob up here in Canada, and some of those cold temperatures are actually sort of leaking into Nevada as well. Okay, let's give you an opportunity to try your hand at it. Here is a map of the United States, and what we have here are an array of temperature data. So you can see that we've got a bunch of different temperatures to organize, and all we have to do here is draw some lines to separate values that are different from one another. So I see that there's a big pattern here at the bottom. We've got 103 degrees in Baja, California, 105 degrees right here in El Paso, and 102 degrees over here where Texas meets Mexico, and 100 degrees in southern Louisiana. So all of those values are 100 degrees or larger. So I'm going to draw a line here separating values that are larger than 100 degrees. 100, of course, is exactly 100 degrees. And then over here in Florida, things are only at 90 degrees. So maybe my isotherm would look something like that. Similarly, you want to separate values that are 90 degrees and higher from values that are 90 degrees and lower. And so you'd have something that looks like that. An 80 degree isotherm would look something like that. A 70 degree isotherm would look something like that. And then the only one that we've got left to do would be a 50 degree isotherm, which would separate those values that are less than 60 degrees from everything else on the map. So that's the way isotherms are drawn, and then they can be used to depict temperature information with ease and beauty. Thanks very much for your attention. This has been another Smart Figure.
So let's talk about why temperature varies. So different places have different temperatures, as we can see. And we need to talk about what are the major factors that cause those temperatures to be different. Well, one of these is the difference between land and water. Water is really good at holding on to heat, and it's really hard to change the temperature up. So land will just always heat up faster than water, and it will cool faster than water. It will just generally change temperature faster than water will. So water has very high specific heat. It takes a lot of energy to raise the temperature, and thus it also has to release a lot of energy to cool back down, which means water doesn't like to change temperature. So just in general, land will heat up more rapidly into higher temperatures than water, and it will also cool down faster than the water will. This means you get you'll see the water areas are the water and places near water are always going to be, if you're during a warm spot, will be warmer, will be cooler than the land, which will warm up faster. And when things start cooling, the land will cool off faster than the water does. So the water will stay closer to the middle of temperature range. So you can see here, if we look at the monthly mean temperatures for Vancouver, British Columbia, and Winnipeg, Manitoba, one is on the coast near the water, it's marine, and one is well inland, it's Winnipeg, that's continental. And that, if you're on the coast, if you're by the ocean, your variation in temperature is going to be much less than if you're in the middle of a continent. So Winnipeg continental gets much bigger swings in temperature. And this is for like being on the ocean or being on really big bodies of water. Some really funny effects from large bodies of water that are small enough to actually change temperature. So the effects we get from the lake here are really strange. But in general, water makes things change temperature more slowly. So here's a short video going over how that variation occurs. But the main idea is that it's harder to change the temperature of water, so places that are on the coast don't change temperature as much.
Hello, Callan Bentley back again for another smart figure. After watching this video, you'll have a better sense of the influence that large bodies of water can have on the land masses immediately next to them. So consider this situation here. This is a cross-sectional view of a land mass and the adjacent body of water. So say that's the ocean there on the left, and we've got a little town right here, basically right on the coast. And then there's another town further inland. And let's go ahead and call the town on the coast something like Coastalburg. And then the town inland, we'll call that Inlandville. So we've got Coastalburg and Inlandville, and basically they're both at exactly the same latitude. The only real difference between them is that Coastalburg is on the coast, whereas Inlandville is inland on the continent. We would expect that the temperatures in these two different locations would show different profiles. So here's a real-life example. This is a comparison between Seattle, Washington, and Spokane, Washington. Seattle, of course, is a coastal town, and Spokane is located far inland, close to the border with Idaho. Now, this is over the course of a year, so basically the little letters on the bottom show the months, starting with January on the left. And you can see that Spokane is really cold in January, whereas Seattle has relatively moderate temperatures. By the time summer rolls around, Seattle has warmed up quite a bit, but Spokane has warmed up even more. So Spokane has gone from more cold to more hot. And then by the time the next winter rolls around, their positions have reversed again. There is a role that water plays, in this case Puget Sound and the Pacific Ocean, that basically moderates the temperature of Seattle, and Spokane lacks that moderating influence. So let's go back to our cartoon city here, Coastalburg, and its neighbor Inlandville. When the sun shines down on Coastalburg, some of that energy from the sun is absorbed by the neighboring ocean. And the ocean has a real capacity for absorbing lots and lots of heat. It takes a lot of heat to change the temperature of water by even a single degree. Whereas the land heats up more quickly and to higher temperatures when heat is added. So we're adding the same amount of heat to Coastalburg and Inlandville here. Some of the heat near Coastalburg is absorbed by the ocean, and only a small portion is absorbed by the land. Inlandville, on the other hand, doesn't have a big body of water that can absorb a lot of that heat, so Inlandville heats up a lot. As a result, our final temperature at the end of the day is around, say, 71 degrees Fahrenheit in Coastalburg, and it's a toasty 89 degrees Fahrenheit in Inlandville. Of course, there are many other factors that contribute to these differences. Earth is a complicated system with many interacting variables. Ocean and air currents, the terrain between the two locations, heat released by the ocean in the winter. Each of these is a variable that contributes to the differences. Let's go ahead and see if you can apply this principle now to a new situation. Let's go across the border to our neighbor to the north, Canada. Two cities, Vancouver and Winnipeg, both on the same latitude right there along the Canadian border. What would you predict in terms of the annual temperature trends for Vancouver compared to Winnipeg? Think about that for a second. Well, hopefully you said that because Vancouver is right there in sort of a Seattle-like situation, right there in a marine setting, that it's going to have that moderate temperature influence. So it'll be warmer in the winter and it will be cooler in the summer. Whereas Winnipeg, far in the interior of the continent, is going to have some extreme lows in the winter, and then it's going to get very, very toasty in the summer. Pretty basic principle. Hopefully you got that. Thanks very much for your attention, and this concludes one more Smart Figure.
And you may have experienced this in small scale. The fact that the land heats up faster than the water. If you've ever been to the beach where the beach sand was boiling, burning hot, and the water was freezing cold. I know I experienced that when I've gone to the beach in the past. That's the same thing. The land heats up a lot faster than the water does. So on a larger scale, places more inland have a bigger variation in temperature than places further away. Now, another one is altitude. Places at higher altitudes have lower temperatures. It's colder up at higher altitude. So here we have La Paz and Concepcion. And La Paz is at a much lower altitude than is at a much higher altitude than Concepcion. It's up in the Andes while Concepcion is lower down. And you can see they have similar temperatures throughout the year. They have similar patterns, but Concepcion is significantly warmer than La Paz is. There's also an effect from geographic position. So if you're on the windward coast of an ocean, which in the US is the west coast of the US, because the wind generally goes from west to east. If you're on the side, if the ocean is on the side the wind is coming from, you're going to get less variation in temperature because the ocean is really stable. Because it's this big body of water, it's not going to change temperature much. So Eureka, Washington here doesn't have a lot of temperature variation compared to New York City, which is on the leeward side. So all the wind is generally coming in from, the continent, from the land. So it has a bigger variation in temperature. Let me get rid of that. Okay, that wasn't it. Well, I just let's see. Yes. Okay. So New York City here, because the wind is going this way, because in general the wind across the United States goes from west to east. New York City is getting its weather from inland, and so it has a bigger variation. Of course, now things on. Another factor that can affect how much temperature varies is cloud cover. Clouds have a high albedo, and they also will trap heat underneath them. So they cool air during the day and keep heat in at night because they reflect air, light, heat from above, but they also reflect heat from below. So that means that on an overcast day, the temperature variation is less than on a clear day. That's why in the winter, when it's clear, it is really cold. The coldest days in the winter are clear days. Because all the heat from the air can radiate away into space. But on an overcast day, you get less heat from the sun, but you also lose less heat out to space. So the variation is less. So here's a short video about the difference between cloudy and clear days.
Hello there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the expected temperature trends, all else being equal, on cloudy days versus clear days. So there's a graph in your textbook that looks something like this, and this is basically showing the temperature at different hours of the day over the course of one day, so from midnight until midnight. And this is on a clear day, so you can see that the temperature starts off relatively cool and then it warms up over the course of the day, cresting sometime mid-afternoon, and then it starts to cool off into the evening and into the following night. Now you can compare that to the temperature trend for an overcast day. And you can see that this curve basically has the same shape. It's dipping down in the wee hours of the morning and it's cresting in the late afternoon. But you can see that the extremes aren't as great here. In other words, the lows aren't as low and the highs aren't as high. Let's take a look at a little cartoon situation here to explain why this might be. So here's the ground and a house and a tree and you and your friend. And during the day, you've got the sun up above. That sun is sending down rays of energy, and those rays are hitting the ground and they're warming it up. And on a clear day, basically, there's no protection from the sun. So it ends up getting pretty darn hot. Now, when night falls on that same clear day, there are no clouds to retard the flow of heat to space. So what ends up happening is some of that heat that the Earth has absorbed during the day ends up being radiated back out to space at night, and there's nothing to stop it. So basically the Earth loses lots and lots of heat on a clear night, and as a result that night will be cold. Let's compare this situation to the overcast day. So we need to draw some clouds in here. So here's a nice cloud layer going across from left to right. Again, we'll take a look at the situation during the day. So we've got the sun. The sun is giving off lots of energy. However, now those beams of energy, some of them are ending up being reflected off the tops of the clouds, which are bright white, and only a little bit of that energy makes it through the clouds and down to the ground. As a result, it's a pretty mild day. It's not very hot. Then night falls, and we still have the clouds, so energy that's being radiated up from the ground basically pulls the same trick. It hits those clouds and bounces off, and more of that energy is retained close to the Earth's surface. A little bit makes it through, but overall, the presence of clouds at night ends up basically resulting in a milder evening. Okay, so if this is the role of clouds in determining temperature on Earth over the course of a day, what would you expect if we went to a different planet that, say, had a thinner atmosphere or a thicker atmosphere? What sort of temperature trend would you expect to see over the course of a day on, say, Mercury or Venus? Well, this is covered in a different chapter of the text, but you'd expect to see something like this. In Mercury, you'd expect to see extremely high temperature swings because Mercury has very, very little atmosphere. So it's plunging to 150 degrees below zero during the Mercury night, and then it's zooming up to over 400 degrees Celsius during the Mercury day. Compare that to Venus, which overall is quite warmer, but look at the day-to-night variation on Venus. There's not much at all. That's because Venus has a very, very thick atmosphere, lots of clouds that basically are retaining heat over time. So that tends to even out or stabilize the temperature. Okay, hopefully that's the prediction that you made. Nice work if so. Thanks a lot for your attention. This has been another Smart Figure.
We can also look at how the temperature is distributed over the world. So if we draw isotherms over the whole world and adjust temperatures to sea level to correct for altitude effects, because we're looking for large scale patterns, we can look at different points in the year. So often what we look at are January and July because they represent extremes of temperature. And this lets us figure out global temperature patterns, where we see that the temperature decreases from poleward from the tropics. So the highest temperatures are around the tropics, where the sun can be directly overhead, and it decreases as you get towards the poles. And we also see that the isotherms shift with the seasons. They move. So in January, the warmer temperatures move south. The isotherms generally move south. In July, the isotherms move north. And the warmest and coldest temperatures we find occur over land. The extremes occur over the land, while the oceans are more stable, less extreme. So in the southern hemisphere, we find that the isotherms are straighter and the isotherms are more stable. This is because there's less land in the southern hemisphere. They also show ocean currents. They get bent by the ocean currents because the ocean currents carry huge amounts of warm or cold water around. And the annual temperature range is small near the equator, and it increases the closer you get to the poles with an increase in latitude, and it's biggest over continental locations. So the middle of a continent near at high latitude is where you see the biggest variation in temperature. So here, for example, is the world's mean sea level temperatures in January. You can see it's coldest over the continents. The negative 40 degrees over Greenland, and up here by the Arctic Circle. The highest temperatures are down in the southern hemisphere, in the southern tropics. And while it's cold, you can see the southern hemisphere, the isotherms are much straighter and more even in the southern hemisphere than they are in the northern hemisphere. And then here is July, where it's coldest in the southern hemisphere. Again, much more stable, straighter isotherms down here, and warmest up in continental northern hemisphere. So in Mexico and in northern Africa and South Asia. So these are sort of the distribution of temperatures and how the temperatures change throughout the year. And so, all the isotherms sort of move south in January, and then they move back north in July. So here's a short video about that variation throughout the year.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe global temperature trends at two different times of the year, January and July. So there are two figures in your textbook. This is the first one. This shows a typical global temperature distribution over the month of January. And then there's another map that shows what July looks like. In both of these images, you see this sort of broad pattern where basically it's warmest around the middle of the planet, around the equatorial regions, and then it's colder towards the polar regions. All right, and then obviously in between there's sort of this nice gradation from warm towards cold through the temperate zones. So that variation in latitude, of course, has to do with the angle of incidence of the sun's rays. So the sun's rays hit directly in the equatorial region. They are more oblique in the temperate regions, and then they are sort of glancing in the polar regions. So the poles are generally cooler than the equatorial region. Of course, that varies throughout the year because the planet rotates around an axis that is tilted with respect to the plane of orbit. So the picture we just looked at was the equinox picture, where day and night are equal for 2 days of the year. But the January and July pictures are more akin to the images up top, which are closer to the summer and winter solstices. So let's go ahead and take a look at those again with that in mind. January up top, July at the bottom. You notice that the warm band has shifted. So in January, the warmer temperatures are more south of the equator, and in July, they are more north of the equator. You'll also notice that land tends to enhance the temperature differences. For instance, in the lower map, you can see that over Africa, over the southwest United States, there are higher than normal temperatures in July because of the effect of land. In a similar way, in Siberia in January, there are much lower temperatures. The presence of land tends to deflect an isotherm towards a more extreme temperature. You could demonstrate this to yourself just by looking at, say, the negative 30 degree Fahrenheit isotherm over North America and see how it dips down over the North American continent. Or the 70 degree isotherm here, how it dips up over the North American continent. You'll also notice that there's more land in the northern hemisphere, so overall temperatures are warmer during the northern hemisphere summer, during July. There's also an influence to be seen in the form of ocean currents. So for instance, the Peru current brings cooler water north toward the equator. So you can see that that bulges those 60-degree and 70-degree isotherms in a northerly direction there. In a similar fashion, the Gulf Stream brings warmer temperatures towards the North Atlantic. So you can see, like right here in this area, that, say, the 10-degree isotherm ends up bulging towards the north at that location. Okay, last question just for review here. Where is the annual temperature range the greatest? Where is the range of temperatures the greatest over the course of a year? Well, you may notice that the equator, even though it has really nice warm temperatures, those temperatures don't tend to vary all that much. So it tends to have a relatively stable temperature regime over the course of the year. Whereas in the polar regions, there's a much greater amount of variation. So like here in the North Polar region, you can see 4 degrees Celsius on the July map, and that is negative 34 Celsius on the January map. Thanks very much for your attention. This has been another Smart Figure.
So that's the end of chapter 16. So I will start chapter 17. Because we still have some time. So we're going to talk about moisture, clouds, and precipitation. Water in the atmosphere. So we'll go over the 6 processes by which water changes from one state of matter to another. And we'll indicate whether energy is absorbed or released in these processes. These are important for the movement of energy into and out of the atmosphere. We'll look at a generalization relating air temperature and the amount of water vapor needed to saturate air. We'll talk about adiabatic temperature changes and explain why the wet adiabatic rate of cooling is less than the dry adiabatic rate. We'll describe the 4 mechanisms that cause air to rise. We'll look at how atmospheric stability is determined and compare conditional instability with absolute instability. We'll go over the 10 basic types of clouds based on form and height. And we'll contrast things like nimbostratus and cumulonimbus clouds and their associated weather. We'll look at the 10 basic types of fog and how each forms. We'll go over the Bergeron process and explain how it differs from the collision coalescence process. These are the 2 ways in which rain forms. If you want to know which one applies here, primarily we have Bergeron process rain. We'll look at the atmospheric conditions that produce sleet, freezing rain, or glaze, and hail. And we'll look at the advantages of using weather radar versus a standard rain gauge to measure precipitation. So, water is, like many substances, has multiple phases it can take. It can have several states. In general, most matter has 3 states that we generally talk about. These are solid, liquid, and gas. And water is the only substance that exists naturally on Earth in all 3 states. Most substances stay in 1 or maybe 2. But water happens to be easily go through all 3 states on Earth. And to change state, heat needs to be absorbed or released. So if you want to change from liquid to solid, generally you need to remove heat, release heat. If you want to go from liquid to gas, you need to add heat. We do these by, if we want to freeze something, we put it in a freezer so it can release heat. We turn it into a gas, we boil it. We put it in a boiler or we heat it on the stove, we add heat. So here is heavy rain and hail at a ballpark in Wichita, Kansas. The 3 states of matter are, solid, liquid, and gas. It requires heat to go from solid to liquid. It requires heat to go from liquid to gas. It releases heat to go the other way. So here are the phase changes of water. And you can actually go directly from solid to gas and vice versa as well.
phase changes of water. In the upper left of the screen, you see two water molecules. The covalent bonds between the oxygen atom and the hydrogen atoms in the water molecule are very strong, making water a stable compound. Notice the polarity of the water molecule. There is a positive and a negative side. Water molecules are attracted to each other because the positive oxygen side of one water molecule is attracted to the negative hydrogen side of another water molecule. In order for water to change states from solid to liquid and from liquid to gas, these hydrogen bonds between water molecules must be broken, and this requires energy. In this animation, we will follow 1 gram of water as it changes from solid to liquid, from liquid to gas, and from gas to solid. The chart in the upper right shows the temperature changes and total energy required in calories as 1 gram of water changes from ice to liquid water and finally to water vapor. You may pause the animation at any time to study the chart and to examine the molecular view box in the lower right. As soon as the ice warms to a temperature of 0 degrees Celsius, it begins to melt. It requires about 80 calories of heat energy to melt 1 gram of ice. Notice that as energy is being added to melt the ice, the temperature does not increase. As you see in the molecular view, in order for the ice to melt, the water molecules must gain enough kinetic energy to move more vigorously and break some of the hydrogen bonds. The energy used to melt ice is, in effect, stored in the liquid water as latent heat. Next, in order to raise the temperature of the liquid water to its boiling temperature of 100 degrees Celsius, more heat must be added. To completely vaporize 1 gram of liquid water at a temperature of 100 degrees Celsius, an additional 540 calories of heat energy are required. This is known as the latent heat of vaporization. In the molecular view box, you can see that the molecules of water vapor are now highly agitated. As the animation continues, we see another phase change, the direct freezing of water vapor into ice. This process is called deposition, or simply sublimation. If the water vapor is at a temperature of 100 degrees Celsius, about 720 calories of latent heat must be released in order for this process to occur. Notice in the molecular view that as latent heat is released and ice forms, the water molecules lose some of their kinetic energy, so that the hydrogen bonds can again form between the water molecules. Next, we see the 1 gram of ice heated and converted directly into water vapor through the process of sublimation. As you see in the molecular view, in order for the water molecules in the ice to gain enough kinetic energy to convert to a vapor, the latent heat of sublimation must be absorbed. As the animation continues, the water vapor changes to liquid water in the process of condensation. If the water vapor is at a temperature of 100 degrees Celsius, about 540 calories of latent heat must be released in order for condensation to occur. Once the 1 gram of liquid water has cooled to 0 degrees Celsius, 80 calories of heat energy must be released as latent heat of fusion in order for ice to form. The sequence of phase changes illustrated in this animation shows idealized circumstances, such as the vaporization of water at its boiling temperature. In nature, evaporation of water can take place when the temperature is far below the boiling point. In fact, the majority of water vapor in the atmosphere is added through evaporation rather than through the vaporization of water at 100 degrees Celsius. In reality, the latent heat of evaporation is slightly different from the total values you see in the animation chart. Understanding the nature of the exchange of latent heat during phase changes is essential to understanding many atmospheric processes. For example, evaporation is a cooling process because latent heat is absorbed, while condensation is a warming process because latent heat is released.
So heat energy is commonly measured in calories. 1 calorie, thermodynamic calories, is the heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. The calories on your food are in fact kilocalories. There's 1,000 thermodynamic calories in a food calorie. And which is why you'll see them on, sometimes I've seen on some packaging, especially on European foods, it's sometimes written as kcals. It's a weird thing that happened. And you'll see lowercase c for the thermodynamic calories and an uppercase c for the food calories. We're only going to talk about the thermodynamic ones in this class. Latent heat. Late means hidden or latent heat. It's called that because when you add heat to something undergoing a phase change, it doesn't change temperature. So if you have some ice and you add heat to it, it melts, but it stays at 0 degrees Celsius. It's heat that isn't derived from a temperature change. There's no temperature change, you're just adding or removing heat, and there's a phase change instead. And it's very important in atmospheric processes because latent heat is a lot of energy. Like these transformations between phases take a lot of energy or release a lot of energy. Just as a comparison, to heat water from freezing to boiling temperatures from 0 degrees Celsius to 100 degrees Celsius, to heat a gram of water through that temperature takes 100 calories. To boil it takes 540. So there's a whole lot more energy required to go from liquid to gas than even to just warm from freezing to boiling. And then to freeze it is 80. It's still a lot. So evaporation. So here are some rough numbers. In evaporation, liquid is changed to a gas. About 600 calories per gram of water are added. This is called the latent heat of vaporization. The amount of heat required varies on the temperature and the pressure and stuff, but it's around that range, 600-ish. Condensation is when water vapor or gas is changed into a liquid, and about 600 calories per gram of water is released when water condenses. This is called the latent heat of condensation. This is one of the ways that heat gets transferred up in the atmosphere. Water evaporates, absorbing heat, and then it condenses higher up in the atmosphere, releasing that heat. So when clouds form and water condenses, it actually warms up the atmosphere around it. Melting is when a solid is changed into a liquid. About 80 calories per gram of water are added. This is the latent heat of melting. And for freezing, the liquid is changed to a solid. That 80 calories of heat is released. This is called the latent heat of fusion. And there are reusable heat packs that use the latent heat of fusion of, well, it's not water. It uses the latent heat of fusion of sodium acetate, I believe. So what you can do is you can set up these things and you can set up these heat packs so that they're in a super saturated, they're like super cooled. They're not going to form solid until they're disturbed. And then they have a little metal popper in them, which disturbs them. And they release the heat they've stored as they turn to a solid. And then you can reset them by basically boiling them, adding heat so that they're reset. And then sublimation. Sublimation is the process where a solid is changed directly into a gas. And so this is where in your freezer, this is how your ice cubes shrink in your freezer over time. They slowly sublimate. About 680 calories per gram of water is added to sublimate. ice. Other things that sublimate, dry ice sublimates. Because liquid carbon dioxide doesn't exist at atmospheric pressure, you need much higher pressures. Mothballs also sublimate. A deposition is when a gas turns into a solid. So when water vapor changes into a solid, this is where that sublimated ice from your ice cube tray deposits on the walls of your freezer as frost. So whenever you see frost is directly deposited solid water from vapor, and heat is released in this process. And again, it's about 680 calories per gram. So there's these transitions. Melting absorbs about 80 calories per gram. Freezing releases about 80 calories per gram. Evaporation absorbs about 600 calories per gram. Condensing releases about 600 calories per gram. Sublimation absorbs about 680 calories. And deposition releases about 680 calories. So there's always this exchange of energy. So this is another review of those changes of state in water, and those drive a lot of things.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe how water can change its state and what the names are for the different processes that describe the different states of change. So let's start with a common phenomenon that happens on my deck every summer. When I pour myself a glass of iced tea and go out and sit on the deck, I notice that the exterior of my iced tea glass starts to develop all these little droplets of water all over it. What's going on here? Well, it has to do with changes in the state of water. So water exists in three states: solid, liquid, and gas. The solid form of water, of course, is called ice. The liquid form we just call water. And then the gaseous form of water is called water vapor. Water can transform from vapor to liquid, or from liquid to solid, or even from solid to vapor. So let's take a look at some of these processes. Let's first consider melting. So this is what happens when ice melts and becomes liquid water. For a single gram of water, it takes about 80 calories of heat to make that transition happen. The reverse transition, which is of course freezing, takes the same amount of energy. So 80 calories of heat are released when water freezes. That might be a little bit counterintuitive to think of water releasing heat when it freezes, but that's exactly what happens. All right, let's consider a third possibility here, and that is sublimation. This is where ice, solid water, goes directly to the gaseous form, and it doesn't go through the liquid phase in between. Well, it takes about 680 calories of heat to be added to the ice in order to get it to sublimate. The opposite is when the gas turns directly into a solid, and that's called deposition. And deposition releases 680 calories of heat. So you can see here that in part of our picture so far, we've been looking at transitions that take 80 calories of heat or release 80 calories of heat. With sublimation and deposition, we've got 680 calories of heat. I bet you can make a prediction here about what's going to happen when we transform liquid water into gas, when we evaporate liquid water. You guessed it, 680 minus 80 gives you 600 calories of heat. So in order to get 1 gram of water to turn into 1 gram of water vapor, you've got to add 600 calories of heat. The opposite phase transition when water vapor turns to liquid is called condensation. And again, that will release that same amount of heat, 600 calories of heat. Condensation is, of course, what's going on with my glass of iced tea. So those little droplets of water on the outside are coming from water that's in the air. You can't see it, it's water vapor, but when it hits that cold surface there, it has a substance to which it can impart that load of heat. So basically the water then releases that heat and it goes from the vapor phase into the liquid phase, coalescing as droplets on my glass. That's a lovely example of condensation. Okay, let me give you two other options. You tell me what's going on. Here's the first one. This is frost, such as might develop on a window pane or might develop on your car windshield after a cold night. So which of the different phase changes is this representative of? Okay, so you're ending up with ice, so it's got to be one of the two blue arrows that go to ice. Basically, this is happening with water vapor in the air, so you're not having a liquid phase. So it's an example of deposition, all right, where we're going directly from water vapor down to solid ice. Very good. Let's check the last one here. There's not much to see here, but this is a foggy coast. Maybe the coast of like Maine or California or someplace like that. You can see there's a lighthouse. This fog is basically a cloud that's sitting on the ground. So which of the phase changes is at work to produce this scene? Well, it's actually just like the glass of iced tea. It's condensation, where you've got vapor that's turning into little droplets of liquid. Those little droplets of liquid make up the fog. They're suspended in the air, so rather than coalescing around an iced tea glass, they're coalescing around little tiny airborne nuclei, little particles of dust and stuff like that. And of course, if the droplets get too large, then they'll fall out of the air, and that'll be an example of precipitation. Okay, so hopefully you got a better sense of the way that water can transform from one phase to another. Thanks a lot for your attention. This has been another Smart Figure.
And just as a general thing, if you can see it, it's liquid water. It's not water vapor. So the steam you see rising off your hot cup of coffee or whatever is actually little droplets of water condensing out of the water vapor that is there. Water vapor is invisible. Yeah, so we'll stop there. Next time we'll talk about humidity, the amount of water vapor in the air. So just a reminder. On Tuesday, we will be having our test on chapter 1 and chapters 21 through 24. It's mostly on chapters 21 through 24. So we'll have the exam. It will be multiple choice in class, and you need a pencil because it'll be using a Scantron sheet and the machine text pencils. Yes.
21. Okay, so they're gonna be like valid or is it certain chapter?
More or less equal for each chapter. I don't know exactly what it is, because I'm sort of throwing trim things out.
Well, except for one.
Well, except for one.
Yeah, except for one.
One is very few. One, there's only like 5. And then there's about an equal number for the rest of them. Roughly equal. I don't know if it's exactly equal, because I'd have to go through and count. Because I was modifying it. I started with equal numbers and then took some away, which means there's slightly different, but there's roughly equal. I was aiming for equal, but I don't know if I actually achieved that. Yes.
For the notes, could we just use any type of paper, like a loose leaf of paper?
Yeah, just any sheet of paper like this size.
All right.
That's all I'm saying.
Okay.
Loose leaf is fine. I'm just